This week, we will study the simple linear regression models. Okay, let's suppose that you run a grocery chain that sells foods, and your business is doing very well. So you certainly want to expand your business. You want to open a new shop in somewhere, say region A, region B, region C, region D. Which place, which location should you choose for your new shop? In order to make an informed decision, you want to understand how household income affect food consumption. You certainly want to locate your new shop into a region, into an area which promotes your sales of food, right? So you want to understand this relationship between household income and food consumption. You start with economic theory. Economic theory and intuition will suggest that the higher income, higher consumption, which makes sense, right? The higher income I have, I'm going to spend more on food, spend more on things that I like. That is, income positively affect households in consumption. We can write this relationship in a mathematical equation like this. Y is household per person food consumption expenditure. X is income, household income. E, we use E to capture all the other factors that affect food consumption expenditures. And F here denotes that it's a function of, here is very general. It could be, we haven't specified the specific functional form yet, but we know that Y depends on X and E. And our economic theory suggests that there's a positive effect from incomes to consumption of food consumptions, which means that this symbol D is differentiation, partial derivative of Y with respect to income must be positive. If it's negative, then that means the higher X, lower Y. But we expect this to be positive. Okay, that's the economic model. Following this economic model, we can then specify in econometric models. So bear in mind that we have this Y is equal to, is a function of X and everything else. Now we're going to specify, we're going to give this F a specific functional form, a linear functional forms. So we're going to specify Y is equal to beta 1 plus beta 2 times X plus E arrow. And you know that I'm going to have subscript I, which denotes observations, the data we have. So here we call Y, it is a dependent variable. X is an independent or explanatory variable, and E is called error terms. So by specifying this econometric model, we are assuming that there is a true value of beta 1 and true value of beta 2 that generate the data we have in hand. So maybe beta 1 is equal to 0.2, beta 2 is equal to 0.8, but we don't know them yet. So we want to use data to estimate what beta 1, beta 2 should be. So this model is called a simple linear regression model. It is simple because it only has one explanatory variable, which is X, household income. That's why it's called simple. Right, so we start with economic theory specified in econometric models. Now we need data to estimate beta 1, beta 2. So let's collect data. To collect data, let's randomly, so importantly, randomly choose a household from the Australian population, suppose. So I want to look at this relationship between household income and the household food consumption expenditure in Australia, suppose. So I randomly choose one household, and then I can call this household, or I can interview this household, asking them, the household head, how much do you spend on food per person? And he or she may answer, say, per person in a week, let's suppose, weekly. My answer say, okay, we spend $100 per person on the food, and then I'm going to ask, so this is our Y. So this is household 1. Then I'm going to ask, what is your household income? And he or she might answer say is $1,500. So now we click one data point, one observations. We do repeat this. Say second house, randomly choose another house, one more household from Australian population. Do the interview, collect the data, so on and so forth until we repeat n times in this 100. So we random samples 100 households from Australian populations, and through interview, through survey, we collect this data. So in the end, we have a sample of n observations in data points. Observe that we do random sampling. This is very important, okay, for our estimation purpose. This means that data are independent. One household, data from one household, we should understand this as a random variables, a realization of random variables. And data from another household, household 2, is another realization of a random variables. Then, because of random samplings, these two data points, they are independent of each other. Okay, they are not correlated; they are independent. We also typically assume that they are identically distributed. They are sampled from the same distribution, and which makes sense that because we are sampling from the same Australian population. Okay. We call this IID, independently and identically distributed. Okay, a data could look like this. So first household spend $155.22 on food, and the income is $369 per week. So on and so forth. So now we have data in hand. So given the linear model, the linear econometric model that we have just specified, and the data, the question now is, how can we proceed to estimate beta 1 and beta 2? Okay, let's plot our data. Remember, we have X, which is income, Y is food consumption expenditure. We can plot all data points on a scatter plot like this. This is scatter plot. For example, there's one household that weekly income is roughly this level, maybe $1,800 per week. Note that the unit for the weekly household income is $100. Then maybe the associate food consumption is $2 or whatever unit it is. So that's the data plot. Okay, so that's the scatter plot. Look at this scatter plot. Would you agree that what about let's draw lines that fits all these data points in the best way? Like this red line. I can draw red line, I can draw another one, this one. So let's draw lines that fit the data points in the best way. And clearly, I hope you agree, there's no line that will pass through all these data points. Remember our data point, look at the data point, we can see that there's a positive relationship between x and y. However, we cannot draw a line that passes through all these data points. Okay. So what do we mean by best way? No matter what line we draw, there's always error. For example, like this point. And suppose I draw this red line. Then this point corresponding to an x level of roughly 5.8. According to this line, go from 5.8 up to lines, we can read out roughly 6. Y should be associated, y should be 6 according to the line that we chosen. However, the data itself go from this one up to data point. It says that it is roughly 7. So there's an error which is roughly equal to 1. So no matter how we draw this line, there's always error. So what about let's choose the line, which means I'm going to choosing beta 1, beta 2 to minimize the sum of square error. Now it's just so there's one error here, there's one error here, there's one error here, there's one error here. I'm going to square them. Why do I want to square them? It's because here for all my drawing here, errors are positive, but error could be negative. This error is negative. This is negative. This is negative. So clearly, if I add positive error with negative error, they will cancel out, which is not good. So I'm going to square them first. So to get rid of the signs, and then sum them up. So I'm going to choose a line or choose beta 1, beta 2 to minimize the sum of these squared errors. So in mathematical form is this. So choosing beta 1, beta 2 to minimize this objective function S, which is sum of square error. E is the error squared, and this sigma sign, it says that okay, it's a compact way of writing the sums. It's just E1 square plus E2 square plus E3 square plus En square. Okay, then again, you remember that, let me remind you that we have this, the econometric model we specifies yi is beta 1 plus beta 2 xi plus ei. That means that ei is equal to yi minus beta 1 minus beta 2 xi. Okay, then we plug this one into here. Solving these minimization problems. So I'll show you the technical, the way to solve this problem later on. We can derive the estimator of beta 1 and beta 2. And we call this ordinary least square estimators. So that's the estimator beta 1 and beta 2. And for for the time being, you might be wondering, where do they come from? I'll show you later on. Okay. Just observe here. Now you want to observe that B1 and B2, they are random variables. They are function of data, and data themselves are random variable or realization of random variables. So B1, B2, they themselves are random variables. The true value beta 1 and beta 2, they are not random variable. They are true value for unknown to us, and we use B1 and B2 to estimate them. So B1 and B2 is a function of data, so they are random variables. In principle, so we have this formula now. We have that formula for B1 and B2. In principle, we can compute B1 and B2 by hand. In practice, well, we use statistical package like R to do the regressions, to run the regressions. That make your life easier. So we want to load data onto R and use an inbuilt command in RLM to run a regression. So in the next videos, I'll show you the estimation implementation of the estimation in R. Right, below is the regression output. So here, intercept is the beta 1. Income is the coefficient of income, which is beta 2. Estimate beta 1, okay, it's actually B1, so B1, B2, which is estimate of the beta 2. So now we have actually estimated the model to be this. This is B1, this is B2, and B1 is estimated to be 83.416, B2 is 10.21. Now the question is, what do we use this for? How can we utilize this information? Typically, we are interested in answering two types of questions. One is, what if? If income increased by $1, how much will food expenditure change? Or if income increases, will the food expenditure increase or decrease? Second type of question is forecast. We wish we can use this information to predict the level of food consumption expenditure. For example, we can answer, if income is $1,000 per week, what is the predicted food expenditure? How many dollars? Right. So here we need to be careful about the units here. Unit Y is, remember, Y is food consumption expenditure. The unit is dollar. Unit X, which is weekly household income, is $100. Okay. So we can differentiate this equation with respect to income. So marginal, to get the marginal impact of income, differentiate Y with respect to X, which is 10.21. This means what? This means if income goes up by $100, income goes up by $100, which means the unit of X is $100. Okay, so that means X increased by 1. Then food expenditure increase will be 10.21 times 1, which is $10.21 on average. Okay, if income rises, will the weekly food expenditure increases? The answer is yes, because our B2 estimate B2 is positive. And we actually need to conduct hypothesis testings. We will do this in the future. Forecasting. If income is $1,000. Then we can predict food consumption expenditure as 83.416 plus 10.21 times 10. Okay, bear in mind it's 10 because unit of household income is 100. So this is 10. So we get $185.516. That's our predicted food consumption expenditure. In interpreting the regression results, we need to distinguish between causality and correlation. Typically, we want causality rather than correlations. That is our model causal or predictive or both? In the regression context, we got to be careful about this. We actually cannot definitely say that X causes Y unless the set of assumptions that we will talk about later on holds. For example, in our model, there may be other factors missing from our simple linear econometric models, which also provide information about the data generating process. Okay, let me finish this videos by have a brief discussion about functional forms. So previously we estimated simple linear models. So y is a linear function of x, and marginal impact of x on y is just this coefficient beta 2. We can also specify quadratic functions. So for example, if our data look like this, then a quadratic function like this might be a better fit. And so here x is x raised to the power 2. That's why it is called quadratic functions. And now the marginal impact of x on y is differentiate y with respect to x. We get 2, bring the power down to 2 beta 2 times xi. So now the slope, the marginal impact, really also depends on x, the income levels. So that's a quadratic model. We can also have what is called semi-log linear model. So the dependent variable is log y, is a log function of y rather than y itself. It's equal to beta 1 plus beta 2 x1. So in these cases, the marginal impact differentiate log y with respect to x, we get a beta 2. And here we can also calculate what is called elasticity, percentage change of x. If x increased by 1%, what will y change by how many percent? And it's actually equal to beta 2 times x1. Okay, that's elasticity. We can also specify what is called log linear model. So now the dependent variable is in logarithm form. The explanatory variable or independent variable is also in log forms. So here, the elasticity is very easy to calculate. Differential log y with respect to log x, we get a beta 2. This is elasticity. And here, beta 2 can be interpreted as if x increased by 1%, y will increase by beta 2%. Okay, this is how we can specify a simple linear regression models and collect data and estimate the models and interpret results, use the information we have from the estimation to inform us in business decision making.